All right, chapter 24, last chapter. So this is organic chemistry. It's just an introduction to it. So the usual credits here go to Zumdahl's chemistry and Brown LeMay's chemistry. Use both of those in preparing this, as well as also some other sources. The commentaries provided by myself, and also a lot of the notation in this chapter is stuff that I put in there in addition to what was already there, that I've edited that was already there. Next slide. Here's the picture for Zumdahl. This is the book we used to use before Brown LeMay. They're both very good books. Next slide. And again, a lot of this stuff that is edited and added in here is from the author, although some of it has been removed so that this would be a shorter presentation. So you'll want to look, if you have time, at the full set of notes that I provided in Canvas. Next slide. Next slide. So the big deals here are listed. I'll let you pause this and look at this if you want to. Next slide. All right, so organic chemistry is the study of things that contain carbon. Biochemistry is the study of living things. So what we're going to do in organic, if you take it, is start off kind of like at the level that you'll end up with in general chemistry, although 1412 doesn't really lead naturally into biochemistry or organic chemistry, but anyway, but you will learn some things in, especially 1311, I guess, and some things in 1412 that will be stuff that you'll keep going back to when you take organic chemistry. When you take organic chemistry, you start off with alkanes, and then you kind of build up, and then in the second semester, you get over into things like carbohydrates and peptides and proteins, and nucleic acids and that kind of thing, and that leads naturally into biochemistry. So that if you've taken organic chemistry, then you can really go into biochemistry just like it's just a natural process. So when we say carbon-containing compounds is organic chemistry, we're excluding things like diamonds, which are carbon, or pencil leads, which are carbon. Those are considered to be inorganic. But it turns out that there are a heck of a lot of organic chemicals, things that contain carbon, because carbon can make 4 bonds and make really long chains, and so it gives you an almost infinite variety of different ways that it can be constructed. Next slide. So starting off here with hydrocarbons, hydrocarbons just have hydrogen and carbon. So what we're going to do at the beginning here is we're going to leave off things like oxygen and nitrogen, and then we'll bring those in later. So hydrocarbons basically are divided into 3 main kinds. Alkanes would be the first one that we're going to look at. And alkanes means that you have a hydrocarbon and you don't have any double or triple bonds. So your formula will always be that whatever the number of the carbons is, which for here, this example, there would be 2 carbons, you would have twice that many hydrogens plus 2. And the plus 2 comes from the ones that are on the end. So your general formula for alkanes is going to be that whatever the number of C's are, multiply by 2 and add 2, and that'll give you the number of H's. Next slide. All right, so if you, on the other hand, and we haven't gotten to this yet, so this slide maybe is a little bit out of place, but if you have hydrocarbons that have a double or a triple bond, they're considered to be unsaturated, whereas saturated would be where you don't have any double or triple bonds. And sometimes you'll hear discussions, right, about the difference between saturated fats and unsaturated fats, and anyway, so I'll leave that to the people that study that kind of thing. So, for example, here on the left, we've got a compound that has a double bond, and on the right, we have something that has a triple bond. So these are considered to be unsaturated. Next slide. And also we want to remember that, and this is important, that a double bond consists of one bond that goes directly between the 2 nuclei of the 2 atoms. So like here are the 2 nuclei, then you have one bond and only one bond that can go directly between them. So that means that if you have that bond already in place, then the only way you can get a second bond would be to put it above and below, or you could put it in and out of the screen if you wanted to have a triple bond. So the one that's in the middle there, the sigma bond, will tend to be strong, and it tends not to break unless you really do a lot to it. But the pi bond on top is not that hard to break, and so it's easier to get a reaction if you have something that has a pi bond. In other words, if you've got a double bond, and it's true to some extent with a triple bond, I mean, when we talk about alkenes, we'll talk about this, but when you have a double bond, it's much more reactive, much more reactive than a single bond. So that doesn't mean that a single bond can't react. It just means that it's more difficult to get it to do so. Let's go on to the next slide. So there are two main types of isomers, structural isomers and stereoisomers. Structural isomers means that it's put together differently. So for example, you could have a carbon that has a molecule that has 4 carbons in it that could have either all 4 of the carbons in a row, or you could have it where you have 3 carbons in a row and then you have another carbon stuck on the middle carbon, but they're both still going to have the same chemical formula. But they're not the same thing. In the old days, they would have been called normal butane and isobutane, because the one in the middle the one that has the carbon in the middle is not structured the same way as the one that's just straight. So that's a structural isomer, and they're pretty easy to identify. You just have one structure versus a completely different structure, so the connectivity is different. On the other hand, you can have another kind of isomer, and it's called a stereoisomer, and that means it's oriented differently in space, but it has the same connectivity. In other words, it has not only the same chemical formula, but it also has these atoms put together in the same way. It's just that they're oriented somehow in space differently. And so an example of that, if you're familiar with this, would be if you have a double bond and it has 2 different things on both sides of the double bond. And so there are 2 different ways you can orient those. You can have them so that, for example, the 2 small things like the H's are on one side of the double bond and the 2 larger things are on the other side, in which case you'd have what we call cis. So I won't go through that now because we're going to go through it later. But that's a type of an isomer that's not a structural isomer, because the structure is the same, but it's still not the same 2 molecules. They're different somehow, and you can't grab them and twist them around to make them the same. So those are called stereoisomers. Now, if you can grab them and twist them around and make them the same, then they're not isomers at all. They're the same molecule. Okay, so I think you'll begin to see that as we go through this. Next slide. So the second main kind are called stereoisomers, where stereo refers to the fact that they're oriented differently in space, but they're still going to have the same chemical formula, and in this case they're also going to have the same structure, but they're not the same molecule. Do you see the difference here? So all the isomers can either be classified as stereoisomers or structural isomers, and then also stereoisomers themselves can also be broken down into 2 main categories, and those are, number 1, enantiomers, which is a special case where you have what's called a chiral carbon, a CHIRAL carbon, that has 4 different things attached to it, and they can attach in different ways. So you have exactly the same thing, but it's just that they're mirror images of each other. That's called enantiomers, and that's one main category all by itself, just that one thing. And then the other main category is called diastereomers, and that has a lot of things in it. The ones that we're going to worry about in this class, and the main ones, are cis-trans isomers, which are called geometric isomers, and then what are called conformers, which we'll look at very briefly. You'll study it in great detail if you take organic. And then there's also what are called conformers, which are things like chair-boat configurations, which typically would be something you would see if you have a cyclic alkane or something like that. Let's go to the next slide. So we just said this, but let's review. Enantiomers are one main kind of stereoisomer, and diastereomers are also another main kind of stereoisomer. So we said isomers can be broken up into structural or stereo. Now we're saying that stereo can be broken up into 2 main categories, either enantiomers or diastereomers. Now don't let the stuff on the next slide fool you, because it's going to seem like it's giving you a different way to classify them, but it isn't. It's just picking out 3 things that are already in the things that we've discussed, and it's telling you about those things, but it isn't giving you like an alternate classification system. So let's see. Enantiomers, let's talk about that for a moment. Enantiomers here, I'm right here, are stereoisomers that are non-superimposable mirror images. They have it isn't here, but they have a chiral carbon, which means there's a carbon there that has that has 4 different things attached to it. So chiral carbon, CHIRAL carbon, means there are 4 different things attached to the carbon, like you'd have H, F, Cl, and Br. or you could have H, CH3, and then ethyl and Br, or something like that. So whenever you have a situation like that, you can have mirror images, but you don't necessarily have them. It depends to some extent on how many chiral carbons you have in the molecule. But on the other hand, to go in the reverse direction, if you want to have enantiomers, you do have to have one at least chiral carbon. The other kinds of stereoisomers are all grouped together in what are called diastereomers, like geometric or cis-trans. The other ones are listed down here at the bottom, rotamers and conformers. So we'll look at that. So let's go to the next slide. So here, this is the same thing that we've been saying. It's just kind of giving it to you in a chart. So on one side, we've got structural or constitutional isomers, and on the other side, we have stereoisomers, which can be broken up into enantiomers and diastereomers. And then the diastereomers can consist of, among other things, geometric isomers or cis-trans isomers, conformers, which are not shown here, we'll look at them later, and then rotamers look like this, where you're looking at the molecule from the end. So this is actually right here where I'm trying to put the marker. That's actually supposed to be a carbon atom, and this is supposed to be a carbon atom, and then the circle behind that on both sides is supposed to be another carbon atom. So you're looking at not only the things that are sticking off of the back carbon, but also the things that are sticking off the front carbon. And so you can see here that these are the same. These two things are the same. It's just that they're rotated differently, where here you have these things in the position where the two methyl groups are right next to each other, where here the methyl groups are directly opposed to each other. And there are names for those configurations, which we don't need to worry about right now. So these are called rotamers. Conformers we'll talk about in a little while. Let's go to the next slide. Now this slide looks like it's giving you a different kind of way to kind of like classify things, but it isn't. It's just talking about some of the things we've already talked about. And it's just giving you kind of like a definition. So conformational would be the things that we're going to mention later when we're talking about cyclic alkanes. Optical would be the enantiomers. So this is just kind of a repeat. Maybe I should have just pulled this whole slide out. Let's go to the next slide. All right, so butane is what we call a carbon compound that has 4 carbons in a row with hydrogens, and no O's or F's or anything else like that, just C and H. So when it's all in one chain, it's called normal butane, and that's abbreviated as N-butane. When it's like this is an isomer. It's a structural isomer of butane, right, where one of the carbons has been taken off the end and stuck in the middle here. So is that really butane? Well, it depends on your school of thought. In the old days it was, because it had 4 carbons, so they just called it butane, but they put iso in front of it. But nowadays, the new system for naming says that this is really a propane, because it's really got 3 carbons in its longest chain. So according to the modern system, you would call this a propane with a methyl group stuck here. So you would call this 2-methyl propane. Or, I mean, really, that's the only way it could be, is if it's in the 2 position. But anyway, you still put the 2 there. So 2-methyl propane. Anyway, regardless of which way you name it, these are both 4 carbon compounds. So their formula would be what? Well, let's figure it out. If you have 4 carbons, then how many hydrogens would you have? You'd have 4 times 2 plus 2, which is 10, right? So you can count them if you want to. They both have 10 hydrogens. So they both have the same chemical structure. Next slide. Okay, so this is what I was talking about before when I was talking about conformers, another kind of diastereomer. In this case, we have 6 carbons, so it's hexane, but they're in a ring. We'll talk about this later. So when they're in a ring, you call it cyclohexane. And you lose 2 of the hydrogens where the ends are, because they have to go in order for these things to link up. All right, so this is a cyclohexane, and this is a cyclohexane, and they're both cyclohexanes. They both have the same chemical formula, and they both have basically the same structure, except that this one's bent up at the top on this side, and it's bent down on this side. So that's called the chair configuration, or conformer, whereas here both sides are bent up, so that's called the boat configuration. And so even though they can convert back and forth, they still exist temporarily, either as this way or this way. So we consider those to be 2 different isomers, which are called conformers. are conformers. Next slide. So let's look at alkanes. Alkanes are defined as things that don't have any double bonds or triple bonds in their hydrocarbons. Next slide. So alkanes are hydrocarbons and they contain only single bonds. No double bonds are present, no triple bonds are present. The general formula is CnH2n plus 2. And an example would be a 3-carbon compound, which would be here would be called propane. You don't have to put N in front of this because there's no way it can be any other way. All right, so there's a list of these different things, and so going from 1 to 10 carbons, it's methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. So you'll just have to memorize those 10. That's all you should memorize. Next slide. So next slide. You just add the suffix A and E to the Greek or Latin root. Some are Greek and some are Latin. It doesn't really matter. So hex would be for 6, as we said. If it's a substituent, like for example, if you got C2H6 and you take one of the H's off, and I'm reading from the bottom here, if you take one of these H's off of the C2H6 and make it into C2H5, and then put it on another larger molecule, then you would call that not ethane, but ethyl. Same thing for methane and methyl. Less frequently, you would see propyl or butyl. So that would be from propane and butane. Next slide. So to name alkanes, you want to first of all find the longest chain. So here, notice that we start here. We start counting with this carbon right here, and we go straight across. We could include this carbon here, but if we did, we'd get a shorter chain. So we don't include it. We just go straight across to 6. So 1, 2, 3, 4, 5, 6. So this is going to be a substituent methyl group. What we want to do here is we want to start from the end to count. That is going to give us the lowest number for our methyl. So if we start on the left-hand side where the 1 is, then we're going to have 1, 2, 3, 4, 5, 6 carbons. So it's going to be hexane. And it's going to be methyl hexane because we've got a methane on here. But do we start at the left or the right to count? Because if we start at the left, we get 3 methyl hexane. If we start at the right, we get 4 methyl hexane. So the rule here is that you start at the side that's going to give you the lowest numbers. And that's only for alkanes, because when we get to alkenes, we're going to find that you don't have any choice really, because you have to start at the end that will give you something else, which I don't want to confuse the situation. So let's wait until we get to alkenes to talk about that. But for alkanes, you start at the end that gives you the lowest number. And now here we only have one thing to worry about, but what if you have more than one thing? Well then, if you have, for example, a situation where you have a choice between 2, 2, 3 and 2, 3, 3, like let's say you have 3 methyls. One possibility is 2, 2, 3, as opposed to another possibility, which is 2, 3, 3. You choose the 2, 2, 3 because of the numbers total up to be less. Next slide. And then you put in the alkane name. So for example, here we've got a 6-carbon compound, so that's going to be a hexane. That's going to be the base name of it, just hexane. So 6 carbons is hexane. We got something stuck on it, then we add that at the beginning. So here we have 1, 2, 3, 4, 5, 6 carbons in a row, and it won't make it any longer if we try to go this way or whatever, or this way. Sometimes the way they'll draw them, though, that will actually make it longer. So we have our main chain here is going to be 6 carbons, so it's going to be a hexane. And then we have 2 methyls stuck on it. And in this case, it turns out, you can look at this, but I think you'll agree with me that it doesn't matter if we start at the left or the right. We're still going to get 3, 4. So it would be 3, 4 dimethyl. And so the reason you write the di in there is because there are 2 methyls. So instead of writing it as 3 methyl, 4 methyl, you just write it 3, 4 dimethyl. So we'll practice that. All right, so let's go to the next one. So here's the list, which I'll let you look at. You can pause it if you want to. So it's methane, ethane, propane, and so forth, as we said before, and you can see the molar masses are getting bigger, obviously. Here are the formulas. And then the melting points and the boiling points are changing in a kind of a linear fashion. Also, the number of isomers goes up dramatically as you get bigger and bigger molecules. Next slide. Let's name these. So here's a good example, and this is the kind of thing you'll see on my exam and also in the final. So let's start here at the left just to get the longest chain, and then we'll figure out if we should start at the left also to do the numbering. So 1, 2, 3, 4, 5, 6, and I don't see any other way to do it that gets it longer than that. So we're going to have our basic long chain is going to be 6 carbons, right? So what's the name going to be? What's the base name going to be? It's going to be hexane, right? So we have a hexane there, and just where I have that line drawn, what all is sticking off? Well, we've got 1, 2, 3, 4 methyl groups sticking off. So we're going to have a tetramethyl situation here with tetramethyl hexane. So what we need to do is find the numbers that will be the lowest combination. So if you look here, you can either have 2, 2. If you start at this end, you'd have 2, 2, 4, 5. If you start over here on this end, you're going to have 2, 3, 5, 5. So that would be larger than the other one. So we want to start over here on the left and go 2, 2, 4, 5 tetramethyl and then hexane. So 2, 2, 4, 5 tetramethyl hexane. Okay, so that's what you're likely to see. I mean, almost guaranteed you'll see something like this on the final exam from this chapter. Let's do B. Now we don't want to start right here on this one because we've got another thing that's kind of deceptively put in here, and it also is on the bottom, but it would give us the same result. And we can go either direction, either branch here, it won't matter. So let's count. We've got 1, 2, 3, 4, 5, 6, 7, 8, the way I'm counting it, and we'll get the same thing if we start here, or if we start here, we're still going to get 8. 1, 2, 3, 4, 5, 6, 7, yeah. So this is going to be an octane. So you can go ahead and write that down. So just kind of put it over to the right of your name where you're going to write it. So put in octane, because that's what it's going to be at the end. And then what substituent groups do we have? Well, the way I have it drawn here, we've got this ethyl group here, and we've got this ethyl here, and we've got this methyl here. And again, what we want to do is start so the numbers are the smallest. And that's going to happen if we start on this side, which I'm going to call the left side, because we're going to wind up with 3 methyl, 3 ethyl. So that's 3, 3, and then 4, 5, 6 ethyl. And it wouldn't matter if you did it where, I mean, if you went this way instead, when you counted them, you'd still have the same thing. So if you do it that way, you're going to have, let's see, 3, 3, 6. Whereas if you start over here, you're going to wind up with 1, 2, 3, 3, 6, 6. So that would be a total number that would be larger than if we started on the left. So, I mean, actually, I think it's easier to do this than it is to explain it. So we want to start right here. And so what we have is 1, 2, 3, 4, 5, 6, 7, 8. So we have octane, and we have a methyl group on the 3 carbon, 1, 2, 3. And we also have an ethyl group here. And then we have another ethyl group on the 6 carbon. So we have 2 ethyls, so that's going to be diethyl. And then we have 1 methyl. So what we've got is 3 methyl, 3 ethyl, 6 ethyl octane. But we don't want to write it that way. We need to change a couple of things. So first of all, because we have 2 ethyls, we want to change it from 3 ethyl, 6 ethyl to just 3, 6 diethyl. And then the methyl is okay. And then the next rule is we want to put these in alphabetical order. So when you're putting them in alphabetical order, you don't care about the dis and the tris and the tetras. So just forget about that. All you care about is the ethyl and the methyl part. And ethyl comes before methyl because E comes before M. So you want to put the ethyls first. So you want to put 3, 6 diethyl and then a dash and then 3 methyl and then octane. And that's the answer. Next slide. Okay, so let's go to the next slide. So here are the most common substituents. So methyl is CH3, ethyl is CH2CH3, and so forth. And then there are some others. When you get down to the propyls and the butyls, it gets more complicated. But I'll let you look at that. You'll really get into that more in organic chemistry. Next slide. And I'll let you pause this and look at this if you want. Next slide. All right, so do alkanes react? Not really. You have to kind of make them react. I mean, you have to do things that are kind of like drastic, like set them on fire. But they can be set on fire, which is called combustion, as you know. And then also it's possible to make them react in such a way that you can actually do a few things, like you can remove a couple of the H's and make it into an alkene, which is called dehydrogenation, or you can actually substitute a H with a halogen like bromine or chlorine. Let's go to the next slide. So that's called substitution, and then I think we've already mentioned the other two, so let's go to the next slide. So combustion. So what happens if you combust something, you burn it? You'll have to, I mean, I realize you understand what it means to burn something, but think about it chemically. What are you actually reacting? Or is it a reaction at all? Yeah, well, it turns out it is. What you're doing is you're taking the hydrocarbon and you're actually reacting it with oxygen. It just puts out a heck of a lot of heat when you do it. So whenever you do this, you always end up with the same two products, CO2 and H2O vapor. And so I'm underlining those right now as we speak. And so when you balance these, you always want to leave the O to the end, because since it's O by itself, you can just write in any number you need. So always start with the C's. So for example, when you start off here, you've got 4 carbons. So you're going to want to initially write down 4 CO2s. Now it turns out in this case that won't actually balance it because of the waters. But so then look at your H's here. You're going to wind up with 5 H2Os. And you notice here that we can't actually get it to work unless we double those. But most of the time you can. So most of the time what you can do is just simply look to see how many carbons you have. If you have 4 carbons, most of the time you can just write 4 CO2. And then if you had, and the reason this one's maybe coming out not exactly right, well, is because of the way the numbers are. But if you typically have 10 H's, you would expect to have 5 H2Os. Now, I mean, you could write it that way. And so, I mean, if you wanted to get rid of the 2 and the 8 and the 10, you could do that. And that's actually the way that I would probably do it. So I would write this number right here as 5. And I don't want to spend a lot of time on this because it's just not worth it. But you could write that as 4, and you could write this one as just 1. And so just leave that off. If you do a 13 over 2 here, and that's the way I would probably just do it. If that's written as 13 halves O2, then you're good. You would wind up with 4 here and 5 here. So why did they multiply everything by 2? Just because they want to get rid of this fraction right here. Okay, anyway, to balance them, leave the O2 to the end. If you've got 4 carbons on the left, you want 4 carbons on the right, basically. And that's what they did to start off with. And if you've got 10 hydrogens on the left, you want to have 10 hydrogens on the right, which means you want to have 5 waters. Okay, anyway, let's go on. Substitution. So substitution here can occur if you shine a light on an alkane and expose it to something like Cl2. The way that they indicate that you're shining a light on it is to write H nu, where H is Planck's constant, nu is the frequency. If you multiply those, you get the energy that you are going to get out of the light that you're shining on this thing. So which kind of light you're shining is going to depend on the particular reaction. But notice here, you've got to do something to this to make it go. So if you just stick the Cl2 and the CH4, it probably isn't going to react, because alkanes, as we've said several times, are not particularly reactive. So if you put the Cl2 with the CH4 and shine a light on it, then you can get it to react in 4 steps, where each of the hydrogens in turn is replaced by Cl. Every time that happens, you end up with an HCl over here on the right. All right, so this is a second reaction, and there's one more. Let's go to the next slide. And that's dehydrogenation, which will take a second to talk about this. So notice here we've got ethane, and we're exposing it to high temperatures and what's called an oxidizing agent. If you take organic, you're going to hear this a lot. So Cr2O3 is an oxidizing agent. And there are 3 different ways you can define oxidation. And they're listed at the bottom of the slide here if you want to read it later. But when you expose it to high temperatures and this oxidizing agent, 2 of these H's are going to come off and leave just a double bond in their place. So you wind up with ethene or ethylene. So you've changed ethane, which is an alkane, to ethene or ethylene, which is an alkene. And then you get the H2. And that's just the 2 H's that you took off. All right, so let's talk a little bit more about what it means to oxidize something. So in chapter 20, we said that oxidation is a loss of electrons, right? But it can also be considered to be when you add oxygen. In fact, that was its original definition. And then actually after that, the next definition they came up with was, you don't have to add oxygen. You can just take away hydrogen. And that's what's happening here, right? So this is actually being oxidized in the sense that it's losing oxygen. I'm sorry, losing hydrogen. It's losing hydrogen. So according to one of our three definitions for oxidation, this is an oxidation process right here. So when you add this oxidizing agent, it wouldn't have to be this one. Any oxidizing agent along with these high temperatures, then you produce this kind of reaction, and it's called a dehydrogenation reaction. Okay, and that wraps up our reactions. Now when you get to alkenes in organic chemistry, you're going to discover that there are a lot of reactions, like 20. And you have to understand all of them, and it's just a pain. So you can look forward to that. Next slide. And then cyclic alkanes are when we take one of these like chains of alkanes and join them together end to end to make a ring. So you can do that from anything from 3 of them up to 7 or 8 or more, 10. So you can have all of these different things that you're joining into a ring. When you do that, you're taking away the 2 end hydrogens, so your formula drops from CnH2n plus 2 to CnH2n. These two here, the C3H6 and C4H8, for obvious reasons are not very stable, because when you have this kind of sp3 hybridization, you want an angle here of 109, and that angle right there is only 60, right, because it's one side of a triangle. This angle right here is 90, so that's still way less than 109, so there's a lot of what's called angle strain on these two. So they don't really like being here, and they have a tendency to try to break. But this one right here turns out to be just about right. So cyclohexane can be just about perfect if it gets into either the chair conformation or the bow conformation that we talked about before. All right, so let's move on to the next slide. And here they are. So here's our chair configuration again, or conformation rather, and here's our bow conformation. And C6H, let's see, H12 would be stable in either one of these conformations. Okay, let's go on to the next slide. All right, alkenes. Alkenes, the main thing about alkenes is they're much, much, much more reactive than alkanes. Why? What is it about a double bond that makes it reactive? Well, it's the fact that one of the bonds in a double bond is a pi bond, right? Pi bonds react. Next slide. So alkenes are hydrocarbons that contain at least one carbon-carbon double bond, at least one. And their general formula is not CnH2n plus 2, it's CnH2n, which, if that looks familiar, it's because it's the same as for a ring structure. So if you have 3 carbons, carbon-carbon-carbon would be propane, but you change it to propene because there's a double bond here. And this actually used to be called propylene. So when you see the polymer propylene, which is called polypropylene, the name is left as propylene, even though technically it's supposed to be propane, so it should be polypropane. Next slide. So here, C2H4 would be ethane, but if it has a double bond instead of a single bond, then it's called ethene or ethylene. All right, and then when you have more than 3, if it's up to 3, it doesn't really matter where the double bond is, because it's the same thing either way. But more than 3, like 4 and above, you have to put in a number. So this is what I was referring to earlier. You have to write the number where the double bond starts. So here, for example, 1, 2, 3, 4 carbons, so that's butane, but you change it to butene because of the double bond there. It's butene, but that's not all, because we also have to show which carbon the double bond starts on. So in this case it would be 1, so it's 1-butene. If you had 2 double bonds, then it would have to be in the position between 1 and 2 and 3 and 4. That's the only way it could happen. Otherwise you wouldn't be able to have the butene. So that would be called butadiene, and it would be 1,3-butadiene. Let's go to the next slide. So let's name these together. So what's the first step always is to count the longest chain. So let's start. I started at the right because the double bond is closer to that side. And these CH3 sticking off here, there's 3 of them, and they're not going to make any difference in our count. So we have 1, 2, 3, 4, 5, 6 carbons. So this is going to be a hexane, but it's a hexene because we have a double bond, so it's hexene. So you can go ahead and write down hexene if you want to, and that's going to be the base name. And then the substituents, well, they're all the same. They're all methyls. So it's 3 of them, so it's trimethyl. And we just need to put the numbers in. In this case, we don't have to worry about figuring out whether we need to start on the left or the right. It's already decided for us because this is 2 hexene. It's 2 hexene because the double bond here is on the second carbon to the third carbon. You write the one that it starts on. And so we have to start our counting on this side because we want the number where the double bond is to be lower. If we started on this side, we'd have 1, 2, 3, 4 hexene. Well, we don't want that. We want the number to be as low as possible. Well, once we've decided that, we've already decided for the methyl groups as well at the same time, because then this methyl right here has to be 2, this one has to be 3, and we don't have any choice. This one has to be 5. So what we're going to end up with here is we're going to have a 2 hexene with a 2, 3, 5 trimethyl. So that actually comes first. So it's 2, 3, 5 trimethyl 2 hexene. Okay, go to the next one. We have to do our longest chain with the double bond in it. You can't leave the double bond out. So when I'm coming across here at this part right here, it doesn't matter which branch I take. So this is like the same thing we saw before, but they just changed one of the single bonds to a double bond. So the way that I have it drawn here is the way I'd like for you to look at it. So let's count the number of carbons in that longest chain. It's 1, 2, 3, 4, 5, 6, 7, 8, right? So it's octane, but it's octene because of the double bond, and it's 3-octene because you want to start at this end because that's going to give you the lower number for the double bond. So the double bond starts on carbon 3, so it's 3-octene with a methyl group on the 3 and an ethyl group on the this one right here on 1, 2, 3, 4, 5, 6. Okay, so we've got a 6-ethyl and we've got a 3-methyl, and 1, 2, 3, 4, 5, 6, 7, 8. So 3-octene. Okay, so which comes first, the ethyl group or the methyl? The ethyl, right? Because E comes before M. So we're going to have 1, 2, 3, 4, 5, 6-ethyl, 1, 2, 3-methyl, 6-ethyl, 3-methyl, 3-octene. Next line. All right, reactions of alkenes are numerous. We're going to look at a few. Let's go to the next slide. So I've written here that alkenes tend to be more reactive than alkanes due to the presence of the double bond. And you're going to find that out if you take organic the first semester. 2 types that alkenes typically undergo as far as reactions are concerned are things that are called addition reactions. And in those, what's happening is that you're adding 2 things across the double bond. Like you, for example, could add a Cl2 where one of the Cl's goes on one side of the double bond and the other Cl goes on the other side. Or halogenation reactions, which is similar to what I just said. So let's go to the next slide. So addition reactions, H2 is another example of something that you could add across the double bond where you're just taking something that has a double bond in it, like this propene right here, and you're adding H2 across it so that you're going to add an H on this side and replace the double bond part of that with an H here and an H here. So you're going to wind up not with propene, but you're going to wind up with propane. So you're going to put an H on that carbon, an H on this carbon right here, and the double bond goes away. This typically happens in the presence of something like platinum or palladium. And the way that you can think of this is like the platinum provides a surface and the H2 kind of like aligns itself on it. And this is, I'm talking about the H2 before it is reacting. So this is like just H2 in the air or whatever, or in your chamber. And so you just add it, and this would be the platinum. And the platinum is providing like a platform for the H to keep it in a straight line, as it were. Or palladium works also, so you just bring it up here to the double bond, and it will cause those two H's to add across the double bond. So what you wind up with here is propane. Next slide. And you can do the same thing with halogens, as we mentioned before, if you have a double bond. In this case, you don't even really need a catalyst. So one of the tricks to organic chemistry is that you have to try to remember that kind of like detail. Like, for example, here, you'd want to try to remember that you don't need a catalyst for this, because in organic chemistry, they'll actually ask you to write these things out, and it wouldn't be so bad if it was just like this one thing. But it isn't. So, I mean, this is going to be like one of 20 different possibilities or more that you would have. So that's one of the challenging things about organic chemistry, but it's not that bad. Okay, so anyway, so you just have to try to remember that if you add bromine across this double bond, you don't really need a catalyst, it'll just add. And so what's going to happen is, I mean, I don't want to rewrite it, but the same thing that happened before with the hydrogen, this double bond here is going to go away, and you're going to wind up with a bromine on this side, on that carbon right there, and then a bromine on that carbon right there. And so that's going to give you 1,2-dibromopentane. Next slide. Okay, moving on to alkynes. Next slide. Alkynes are like alkenes, but instead of having a double bond, you're going to have a triple bond. So that means that your formula will be CnH2n-2, not +2. And the reason for that is because you're losing for the hydrogens right here. Okay, so here we've got 1, 2, 3, 4, 5 carbons, so that's pentane, but because one of the single bonds is replaced with a triple bond, we call it pentine. And we also have to put the number in, just as we did with alkenes. So start at the end, that's going to give you the smaller number, which would be this side over here. So this would be 1, and this would be 2, so it's 2-pentine. Next slide. All right, so we just said this. So here's one we can name. It's already named for us. 1, 2, 3, 4, 5, 6, 7, 8 carbons, octane. But it's not octane because we have a triple bond. So octane, but we have to put the number in of where the triple bond starts. So if we start on the left, we're going to get 3 octane. If we start on the right, we're going to get 1, 2, 3, 4, 5 octane. So we choose 3 because it's a smaller number than 5. Next slide. And then aromatics. Next slide. Aromatics are things like mainly benzene. Whenever you have something that's an aromatic, it's named that way because of their particular odor. So if you've ever used benzene, which, I mean, we used to use it in the lab when I was an undergrad. We used it a lot to clean things, and then I think at some point they discovered that it's carcinogenic, so maybe they don't do that as much anymore. But you can definitely know the smell of benzene. As soon as you smell it one time, you'll recognize it. So that's why they're called aromatics. They're also they're unsaturated, but the unsaturated double bonds are alternating with single bonds. And when you have something like that, it's called a conjugated system. That's not in here. And you have something called resonance, which I believe we've talked about that before. When we were talking about hybridizations, when we talked about the sp2 hybridization, double bonds can have resonance. And in 1311, we talked about that in the chapter where we were talking about valence bond theory. And you'll remember that we had a picture of benzene there too, and it showed the benzene, which was the 6 carbons, and they were all in a kind of like a cycle. And all the bonds between the carbons were sigma bonds, but the bonds above and below were all pi bonds, but they all joined together. So you had above and below a thing that looked kind of like this, it was just electrons. And the electrons were kind of like free to move around. So when you have a situation like that, it's called resonance. Let's move on to the next slide. And so here's the way you draw that. So notice here that we've got 6 bonds. So here's they don't show the hydrogens. If you showed it this way, this is not benzene. But if you put a double bond here and a double bond here, I don't know why they left these out, and a double bond there, then you would have yourself some benzene. Okay, so the way they usually draw it is like this, and they leave the hydrogens off. So there would be a hydrogen here and on all the other carbons, but they just don't show them because it's not necessary. Anyway, you've got a double bond here and then you've got another one here and another one over here. And so, but it could also be that it would be here and here and here. They can flip-flop. And actually, neither one of these is really correct, because the way they actually exist is they exist in a state where they're all moving around the entire molecule all the time. So the way they usually draw it is not like this, but rather like this down here at the bottom, where they just show a circle in the middle. That's actually the best way to draw it. So it's aromatic because of its odor, and it's conjugated. Whenever you have a system where you have alternating single and double bonds, that's called a conjugated system. And you have what's called resonance. And the resonance has to do with the fact that these electrons can get up in this kind of like, almost like a conduction band in a metal. And they can just like freely move around. So they're like almost like a continuous set of electrons going around the molecule. Next slide. All right, so it turns out that because of this resonance, benzene is not particularly reactive. So it's kind of like alkanes. But you can make it react, kind of like you do for alkanes. You can make it react. And this is something you'll want to memorize, maybe for this class a little bit, but also more so for your organic, if you take organic chemistry. And that is that if you add this FeCl3 in the presence of Cl2, let me say that again because this is the only way you can get this to happen. So if you add the FeCl3, or I mean similar ways, but it has to be something like this, in the presence of some halogen, especially Cl2, then it will actually cause that H right there to come off and join together with one of the Cl here, and the other Cl will actually attach itself right here, as we see over here on the right. So the Cl, notice here, this Cl has replaced the H that was there before. And then, and notice here though, you've got to have, this has to be done in the presence of FeCl3. And of course, you also have to have whatever it is you're trying to add. So what does that mean? What if you didn't have this? If you just added Cl2 to benzene, would anything happen? And the answer is no. So you've got to have this stuff right here. So that's something that you want to try to remember. And then you wind up with your HCl here. Okay, next slide. And then when we're talking about benzene, I'm going to go to the next slide here because it's easier for you to see it. We can also name these, instead of like saying 1, 2, 1, 3, 1, 4 for whatever is on there. It's easier for you to see this if we just go to the next slide. So here, for example, we can call this 1, 3, where we have 2 chlorines actually. We've done this twice now. So assume we did this twice. We put 1 chlorine here and we put 1 chlorine here. So now we have 2 chlorines on there. So we could call this 1,3 dichlorobenzene, right? But usually what they do is they won't do that. They have their special name that they have for this, and that's called meta M dichlorobenzene, where the M means that you've got one space between the 2 chlorines. If they're right next to each other, that's called ortho, and that if they're directly opposed to each other, that's called para. Let's go to the next slide. So this would be a case of ortho or O. This would be like what we saw on the previous slide where you have meta or M, and this would be para or P. So again, you're just looking at the relationship between 2 substituted atoms on benzene. Next slide. You can also join 2 benzene rings together to make naphthalene, which people are familiar with this. It has a very distinctive odor that actually, it turns out that naphthalene is not especially good for your health. It was used in mothballs, and it's like one of those things that people used for years and years without realizing that it wasn't exactly a good idea. Like asbestos was another one. Asbestos was used in various products for, I mean, as you probably know, and so because it was used for a long time, people were exposed to it, and then they wound up getting sick from it, and I mean really sick. And so they have to go into buildings now with respirators and take the asbestos out. So you know, this is kind of the way it is with naphthalene. Naphthalene wasn't maybe quite as bad, but when you have 2 benzene rings joined together, it's naphthalene, and then anthracene would be 3 rings and so forth. And I wouldn't worry about trying to remember these because you probably won't see these on an exam. Next slide. And then derivatives, let's go to the next slide. Let's go to the next slide. Derivatives are just things that we are going to put in, which may or may not include things that you have seen up to this point, like halogens. We've seen that. but these other things, I don't think we've seen any of these. So there are things that mainly involve oxygen or nitrogen that you can add to a hydrocarbon. So remember, hydrocarbon just has hydrogen carbon. So if you add something to that that is in one of these forms, they have special names. And so basically when you take organic chemistry, you'll have a whole chapter where you just talk about alcohols. And when you're talking about alkanes, you'll talk about the halo things like the bromine, the fluorine, the chlorine, and so forth. And then you'll have a whole chapter on ethers. You'll have a chapter on aldehydes. I'm talking about an organic chemistry. You'll have a chapter on ketones. You'll have a chapter on carboxylic acids, and all these things, esters and amines. And then all these things build up to the fact that somewhere in the second semester, you end up putting all this stuff together so that you discover that when you take one of these carboxylic acids and one of these amines and put them on the same molecule, then you have an amino acid. And then you start saying, okay, well, what can we do with an amino acid? And you find out we can put those together in a natural polymer to make a protein. Okay, let's go to the next slide. Okay, so speaking of polymers, next slide. Polymers are large, usually chain-like molecules that are built from smaller molecules called monomers. Next slide. So you can take a whole class in this. It's not particularly interesting. I don't really recommend it, but you may wind up, if you, for example, if you want to be a chemistry major, you might wind up taking it. So when you have something like, and these are the old names, ethylene, remember we said that they've been changed to ethane and propene now. So if you make a polymer out of ethylene here, it winds up being polyethylene. And you've heard of that. That's like sandwich bags. And polypropylene is like the plastic in toys, or the film in toys and things like that. And you can also have vinyl chloride. Vinyl here is an interesting word. It's an old word for special situation, which we don't need to get into. So anyway, you can come down, you can see styrene, polystyrene for foam and stuff like that. So that's where these come from. And so the way that these join together is either going to be one of two ways. And then, so what we're going to do is we're going to talk about polymers, and then we'll come back later to the functional groups because we didn't spend much time on that. So the way that these things form is either one of two ways. Either it's going to do what's called an addition polymerization, or it's going to do a condensation polymerization. We'll look at that in just a moment. The addition polymerization means that you start off with something like this ethylene that has that double bond there. They're very reactive. And so what you'll do is you'll create something called a free radical, and you'll introduce it into this vat. Let's say you have a vat, VAT, that's full of ethylene. You just put in a handful of these little radicals, these free radicals. And a free radical is something that we haven't talked about yet, but it's something that has one electron. And so instead of having a negative charge, you can think of it like an ion kind of, except that instead of having a full negative charge, it has one electron that's unpaired, just sticking out. And it's very reactive because it's an unstable state. So like if you had a C with one electron sticking off of one side of it, that would be a radical, or it's also called a free radical. So when you introduce something like that into this vat of ethylene, it will attack that double bond on the ethylene, and it will cause the ethylene that it attacks, it will then become a free radical. So the double bond kind of like flips, and you wind up on the right hand side of that over here with a free radical. In other words, with one electron sticking out, which then that will go attack another one and another one and another one until you wind up with a whole long chain of them. All the double bonds have been converted to single bonds. And so you just let this go until you're ready for it to stop, and then there are several different procedures that are available to make it stop, which are called termination procedures. The other way that you can that you can form polymers is by what's called dehydration, where you take an H on one of the monomers and react it with an OH on the one that's next to it, and the H and the OH go together to make water, and the water comes off. So water is going to be produced in this kind of a reaction, and then the two things that have the H and the OH on them are joined together. So let's go to the next slide and start to look at this. So first of all, the addition is where you start off with a free radical. So here's a free radical. So notice this is not OH minus. It's OH has one electron sticking off of it, and it attacks one ethylene. So you would have typically a whole vat full of this stuff. It attacks one of them, and the double bond is going to flip over this way, and it's going to make a complete bond between the C and the O here, but now that's going to leave one electron missing over on this side. So now you're going to have a single bond here instead of a double bond. You have one electron on this side, so but now it's the whole thing, including the OH here, is going to be another free radical that's free to now attack another ethylene molecule. So here we have down here at the bottom what we wind up with at the top, and now it comes around here and attacks this thing, and the double bond on this thing flips over and makes a bond between it and the previous monomer here, leaving only one electron over here. So it attacks another one, and so forth. So initiation here would occur when you find some way to prepare some of these radicals and dump them into the vat. Next slide. Okay, the other kind of polymerization, as we said, is condensation polymerization, where you're producing water. So you start off with one thing that has an H and one thing that has an OH, and you bind these things together. They actually react in such a way that you have a dehydration here where the water comes off. So when you do this kind of polymerization, you wind up with water being produced, and that's shown over here at the bottom right. And you wind up here, for example, for this one, and this just for this one, not always, what happens is that this NH bond and this CO bond are converted so that the C and the N end up bonded to each other. Right, so when you do that, you wind up with the thing down here that's shown at the bottom right there. So notice now that the bond is between the N and the C, and so also the C was double bonded to an O and the N was an H. We haven't talked about this yet. Whenever we have a C double bond O, it has several different possible ways it can be named, and that depends on what's on the other side over here. Whenever we have an NH, NaH hydrocarbon molecule, it's called an amine. So, I mean, this is kind of like getting out of sequence to tell you this now, but when you have a linkage like this, it's called an amide, A-M-I-D-E. So actually, I mean, this is actually going to be one of the functional groups you'll want to be able to recognize on the test. Whenever you have a C double bond O next to an NH, that's called an amide. And that's actually what happens when amino acids join together, because the COOH, the organic acid on one of the amino acids, will join to the NH2 on another one, and you'll wind up with this. C double bond O, NH. And then on one side, instead of having what you have here, you would have one amino acid over here and you'd have the other one over here. And so in a protein, that happens over and over again. So you wind up with a polypeptide. It's a polymer, but it's called a natural polymer. And in proteins, it's still an amide linkage, but it's specifically referred to as a peptide linkage. Next slide. So proteins, let's go to the next slide. So here, notice this carbon right here has both the COOH. So since we didn't really talk about this before, let's talk about it real quick. That is C double bond O, and then C single bonded to another OH. So COOH is an acid group. It's called a carboxylic acid. It is an organic acid. It's a weak acid. And then over here we have an amine group. So we have an amine and an acid on this carbon, so it's called an amino acid. And so all amino acids that are in our bodies, there's 20 or 22 depending on who you read, all of them have that same structure right there at the top. They're all the same. So what makes them different is what's down here. Now there's one of them, that this R stands for radix. It's from Latin. It means the root of the molecule. In other words, or some people would say it means the rest of the molecule. It's whatever is stuck on down here at the bottom. So that could be anything from H only to any number of really large different like hydrocarbons with various different functional groups in them. And we'll see a picture of those in a minute. So the thing that makes the amino acids different is this R group. But this top part up here, everything from here up is the same. This carbon is called an alpha carbon, and it's the carbon where the COOH and the NH2 attach. All right, next slide. So proteins are natural polymers that are made up of amino acids. So the monomers for proteins would be amino acids. And their molar masses can go all the way up to 1 million. And they are, some of them are fibrous proteins that are going to be in your cartilage, for example, that will provide structural integrity. Next slide. And then there are also globular proteins that are going to do things like go around in your blood in order to transport and store oxygen, like hemoglobin, or act as catalysts, or fight invasion, or participate in the body's regulatory system, and so forth, and also used in the electron transport chain. Next slide. So here again is our alpha carbon. Alpha amino acids are the ones that we have in our body. They're all the same way. Let's go to the next slide. So, and again, as we saw before, whenever one amino acid joins to another one to make a peptide bond, it does the same thing we saw before, where we saw the amide linkage. So the H here comes off. So again, this is the same thing. We have a condensation here where we're producing water, or whatever you want to call it, and the water comes off. It could also be called dehydration because you're losing water. But you're producing this water, and then this N right here will join across to this C. And you're left with this situation here, which we were earlier calling an amide linkage. And that's true, but if it's in a protein, it's also called a peptide linkage. Next slide. So next slide. Here are the different amino acids. Here are the different 20 that are shown on this slide, and previously they used to say there were 22. So, I mean, I guess it depends on who you read. So notice here, everything on the top here except for the blue for all of these is the same. So what's changing? Just the blue part. Like, for example, here for alanine, you just have a CH3 here, and so forth. So this blue part can vary tremendously, as you can see down here. This one has a long chain. Lysine has a long chain of carbons with an NH3 at the bottom, and then this one over here is a kind of a ring. This one has a benzene ring in it. So what you can do is you can look at these and see what functional groups you have on these. So for example, if you notice right there, you've got an OH in here. On tyrosine, you've got an OH, and also on threonine. So you've got, well, that's 3 of those that have that OH group. What's that OH group called? OH, whenever you see it, that's an alcohol. So if you have CH3OH, that's methyl alcohol. If you have ethane with an OH group, it's called ethanol, and so forth. Propane is propanol. So if you're asked to find all the amino acids in this list that have, for example, the alcohol group, you would find that one right there, serine, and tyrosine, and then threonine. You could do the same thing for the NH group, the NH2 group. Like, I mean, there's probably more than I'm going to point out, but here's an NH3, and here's an NH2, and then there's another NH right there, and then here's an NH2, and then, I mean, here's another one. Right, so you could do that with anything, right? So, and then you could be asked to find the C double bond O group here, and so forth. And that's actually present here and here. And then also you might recognize when you look at this that right there is a C double bond O in H thing, like we talked about before. That's an amide, A-M-I-D-E. So those also would be amides. So let's go to the next slide. All right, so what we'll be doing for the previous slide is we'll be doing that again in the work problem. So we'll come back to that. All right, so level of structures. The primary structure is just going to be the basic chain, the amino acid chain. So that's the primary. Then there's another kind of structure that goes kind of like on top of that, where the chain will either wind itself into a helix And this is kind of like in DNA, but not quite. It's different, and it's only one strand, not two, that wrap themselves around each other, as in DNA. And then there's also another kind called the pleated sheet structure. And you don't have to worry too much about that right now because we're going to look at pictures of it. So this is called the secondary structure. So the primary structure is just like if you have alanine, and then you have serine, and then leucosine or whatever. So alanine, and then you have a bond between it and the next one, which is serine. And then you just have, a whole long chain of amino acids, and that's the primary structure. The secondary structure will be when that chain in turn wraps itself into a helix, as we'll see in a moment, or if it makes itself into a pleated sheet. And then even then, there's still another outside structure, there's actually two more, where either the alpha helix or the pleated sheet can then in turn again bend themselves into a third structure. So at this point, I think it's easier just to look at the picture. So let's go to the next slide. So next slide. All right, so here's a picture of the alpha helix, which looks kind of like, the first time you look at it, it looks a little bit like DNA, but there's only one strand here, and it's actually going in the opposite direction from the way DNA goes. So anyway, but this is one way that they can arrange themselves. So here's your main chain. It's just coming up and around like this. So that would be like your primary structure. And then this thing right here, the whole thing would be your secondary. Next slide. And here's what it would look like. Instead of a helix, it can also arrange itself in a pleated sheet where it just looks like you're going down a set of steps like this. Next slide. And then also it can then, like for example, if you have a helix for your secondary structure here, you can then take that helix and wrap it into a shape like this, for example, to make a globular protein. And that's called the tertiary structure. And then you can take 4 or 3 or 2 of these tertiary structures and put them together, and that's going to be in what's called the quaternary structure. Now, just before we move on, you won't need to know this for the test, I don't think, but just for your information. Next slide. And then carbohydrates can do the same thing. So we'll look first of all at what kind of carbohydrates make up the monomers, and those turn out to be sugars, which we call monosaccharides, which contain either maybe usually 6 carbons, but they don't have to necessarily. They have the same type of structure, and they can be joined together as the amino acids can to make long-chain carbohydrates. So let's look at that on the next slide. So whenever you have a 5-carbon sugar, it's called a pentose, and when you have a 6-carbon sugar like glucose or galactose, it's called a hexose. Next slide. So here at the top are some pictures of some different 5-carbon sugars, monosaccharides. So if you notice, you count at the top, it's 1, 2, 3, 4, 5 carbons in there, and down at the bottom you have some 6 carbons. So 1, 2, 3, 4, 5, 6. So there's, a little bit of a difference here. So examples of 5 carbons would be like ribose. And for ribose, if you take away that O right there, you've got deoxyribose. 6-carbon examples would be glucose, fructose, galactose. Okay, next slide. Disaccharides would be when you took 2 of the things from the previous slide and joined them together. When you join those together, that linkage is called a glycosidic linkage, and I'm pretty sure you're not going to see this on any test in our class. But that's just a C bond O bond C bond between the 2 rings. And then when you have a polysaccharide, it's just that you have like a disaccharide kind of, except you have a whole bunch of the monosaccharides, like you have a whole bunch of the glucoses or whatever. So when you have a polysaccharide in animals, it's called glycogen. And that is one of the things that animals store to provide energy. If you have a long polysaccharide in a plant, it's called starch, and it performs the same function in plants. Next slide. So the glycosidic linkage is formed when 2 sugars come together, and again we have this condensation process where the H comes off one side and the OH comes off the other side and makes water. So again, you're producing water, and you're producing a linkage between that carbon and that oxygen right there. So it winds up looking like this: carbon, oxygen, carbon. that's called a glycoside linkage. And so, for example, if you link fructose and glucose here, you get sucrose, which sucrose is what we use for table sugar. Next slide. Next slide. Okay, and also nucleic acids are also natural polymers. DNA and RNA, there are some slight differences between these two, but otherwise they're very similar. Notice that DNA can have masses of several billion. That's amazing. Next slide. So whenever you have a monomer of a nucleic acid, it's actually composed of three things. So you've got basically the main part is called a base, and that's going to be either a purine or pyrimidine. And then you're going to have a sugar attached to that, and a phosphoric acid attached to that. Next slide. And unlike the proteins that were the alpha helix, the DNA is a double helix. So it has two helices that are wrapped around each other, and they're connected with hydrogen bonds. So the inside part that's connected with the hydrogen bonds is going to be the bases. So you would have a purine on one side with a purine on the other side, or you would have a pyrimidine on one side connected to a pyrimidine on the other side. It turns out that the purines would have 3 hydrogen bonds between them, and the pyrimidines would have 2. Next slide. So then the sugars here. In DNA, you have the same sugars you have in RNA, except that O right there has been removed. In DNA, otherwise they're the same. Next slide. Let's see, DNA, you would have, well, actually for both DNA and RNA, you'll have both of these purines, but for DNA and RNA, there's a difference in the pyrimidines. DNA has thymine, where RNA has uracil. And you can see the structures are very similar, but there's a CH3 group here on the thymine that isn't present on the uracil. Next slide. So this is how they come together. You have the base here, and it's joined to the sugar here, and then the sugar is joined to the phosphate here. So this whole thing together is called a nucleotide. And so the way that you make a nucleic acid is you join these together, and the way that they join together is through the 3' carbon here on one sugar joining to the 5' on another sugar. So that would be this one, but it would be on a different sugar. Let's go to the next slide. So for example, here the 5' here will join together with the 3' on that sugar right there, and it will join the two things together so that now instead of having just one nucleotide, you have 2. So this is called a dinucleotide. Next slide. And then this is what it looks like overall. Notice that your pyrimidines are going to have 2 hydrogen bonds, your purines will have 3. So your bases are going to be here, the green things, and then the sugars are here, and then, sorry, the bases, my bad, the bases are going to be here, the sugars are going to be here, as I said, and then these are actually the phosphates on the outside. So you have a sugar to a phosphate to another sugar to another phosphate to another sugar. Next slide. And I'll let you look at this on your own if you want to. You can pause it and take a look at that. Next slide. Okay, and as we've said before, the bases, the adenine, guanine, thymine, and cytosine all form hydrogen bonds along that middle section, so that you're going to have different numbers of hydrogen bonds depending on whether you've got pyrimidines or purines. Next slide. And then here's another picture of it. So adenine and thymine here, 2 pyrimidines make 2 double bonds. So this is going to be the structure in the middle. It's all hydrogen bonds. And what can happen is if you need to replicate the DNA, or if you need to imprint something on RNA, an enzyme can come through the middle here and open up the stretch of the helix to the point where you need it, and then the strands will separate. And it's easy for that to happen because it's just having to break these hydrogen bonds. All right, I think that just about wraps this up. Let's go to the next slide. So we just have one more thing to do, and that's the work problems from this chapter. So I guess I'll see you in those work problems, and let's go ahead and cut this short for the sake of time. So I'll see you there.